ID, the Future, a podcast about evolution and intelligent design.
What does it take for life to exist? Hello, I'm Eric Anderson, and I'm pleased to have Dr. Howard Glicksman back on our show today to help us understand some of the intricate and precision engineering that's required for us to be alive. Dr. Glicksman practices palliative medicine and is co-author of the recent book, Your Designed Body. Welcome, Howard.
Thanks a lot, Eric. It's great to be back.
Previously on the show, we've discussed the idea, which is quite common now these days, and in fact becoming more common in some circles, that the laws of nature will inevitably lead toward life and living organisms. And you've helped us understand, Howard, that when left to their own devices, the laws of nature, these processes that normally take place without guidance and direction, actually lead to death.
So yes, the laws of nature cause a lot of trouble for the body, for life, and life has to come up with innovations to solve those problems or actually leverage them to be able to survive.
And the same insight applies, I would say, at the very earliest stage of the history of life. Of course, Dr. James Tour has shared a lot of information over the past couple of years about how molecules on their own, just by obeying these laws of physics and chemistry, don't lead toward a living organism. Quite the opposite.
Right, that's right, yeah.
Yeah, and in our prior conversations, Howard, we've talked about two other critical issues. First, how the cell maintains control of its internal volume and chemical content. And then the second challenge that multicellular organisms face of getting oxygen and nutrients to all of the cells that aren't directly in contact with the outside environment. So I want to dive into another topic deeply today, and I definitely encourage our listeners to go back and review our prior discussions. But just very briefly, Howard, describe these two issues for our listeners.
Yeah, very quickly. The issue was how the body deals with water and its solutes, because water and its solutes will move around based on diffusion and osmosis. So the cell's problem is it has to maintain control of its volume and chemical content to survive. But the chemicals inside the cell has high potassium, high protein, low sodium, but the water outside the cell has the opposite, low potassium, low protein, and high sodium. So the laws of nature will make the sodium go into the cell and potassium come out of the cell by diffusion, and water will go in at the same time, and that will kill the cell. So the innovation, the solution to that problem is a sodium-potassium pump, which uses a lot of energy, maybe about a quarter of the energy your body's using right now when it sits around doing nothing. And then at a multicellular level, we have to remember that the total body water, 2/3 of the water is inside your cells and 1/3 is outside your cells. And that's all based on the sodium pump, keeping it where it's supposed to be. However, when you have a multicellular organism, now you have a cardiovascular system that has to have enough arterial blood volume. It has to have blood pressure to send enough fluid to the tissues and feed them with the sugar and oxygen and other chemicals it needs. And the problem you have is that in the capillaries where the arterioles, the blood flows into the capillaries, the hydrostatic pressure, the pressure that blood comes in at, is going to have a tendency to move out of the capillary into what's called the interstitial fluid. And if too much of that occurs, then the amount of fluid in the intravascular fluid compartment will be reduced. Your blood volume will reduce, blood pressure and blood flow, and you can go into shock. So to prevent that, the liver makes a protein called albumin. And albumin does have, carries proteins in the blood, et cetera. But one of its main jobs is being in the blood. It's by osmosis, it holds on to a lot of the water that gets pushed out by that hydrostatic pressure. So we know that if people have a low amount of albumin, they can get too much swelling in their body, which is what I deal with a lot in hospice patients. And basically an albumin level of less than 1 gram per deciliter is incompatible with life. So you don't have enough albumin, it doesn't matter what you have in the cardiovascular system, you can't live without albumin.
Yeah, and I think part of what was so valuable, and again, I encourage listeners to go back and check out those episodes, is just appreciating all of the components that are required and the fact that they have to be in the right place at the right time with the right amount, in the right way, functioning in the right capacity. And so this sort of simplistic notion that I think really underlies part of the evolutionary story that, things just sort of happen. Is really, you really put the light of that in the conversation that we had previously, Howard, as well as in the book. So really appreciate that. So today, Howard, I wanted you to help us understand a little bit about how the body controls sodium and water, because I think you had mentioned to me previously that that's really critical.
Yes, and as we mentioned in our book, Your Designed Body, the control systems they overlap with each other, interrelated, so it's very important. And once again, to remember the cell needs the right amount of water. You have to control sodium and water for the cell because it has to have the right chemical content and volume, right? But the body also has a problem. It has to have enough water so that it maintains enough arterial blood pressure so you can feed the tissues. And so to understand how the body controls the sodium and water, you need to understand the setup with respect to sodium and water in the body. The first thing is to have enough arterial blood pressure. To feed the tissues, you need to have enough arterial blood volume, right? Mm-hmm. But arterial blood volume is 15% of the entire intravascular fluid, because some of that's in the veins, some of it's in the chambers of the heart, the capillaries, and the pulmonary circulation. So only 15% of the blood is actually in the arterial system that feeds the tissues. So in order to have enough of that, then you need to have enough water or fluid in the intravascular space. But the intravascular space, it represents 20% of the extracellular fluid, so you have to have enough extracellular fluid. They're all interconnected. And then the extracellular fluid represents 1/3 of the total body water of the body, so you have to have enough water. So they're all interconnected. You have enough water, it has to be in the extracellular fluid, there has to be enough in the blood vessels. And
sorry, Howard, just real briefly. So just real quick, I know you talked about this previously, but just so we're clear for today. So the extracellular fluid, tell us what that is and define that for us, as well as the intravascular fluid.
Okay, so 2/3 of your water is in your cells, right? The other third is outside your cells. And the reason why it's outside your cells is you have the sodium pump that's always pumping sodium out of the cell and keeping water out of the cell so it stays in the extracellular fluid.
Right. So the point is there's space between the cells. We think of maybe, you got one cell right next to the next cell, next to the next cell. But your point is that we've got 1/3 of our water. Is that what you're saying? That's actually outside of our cells.
Yeah. So 1/3 of the water is outside your cells. Now, of that 1/3 of the water that's outside your cells, 80% of that is between your cells. This is what you're referring to. Okay. Mm-hmm. And 20% is in your blood vessels or in the intravascular space. All right.
Okay, great.
So the key thing that this is from the other talks, though, basically you have to remember is that the interstitial space where the fluid is around your cells is a bridge between the blood vessels or the capillaries and your cells. So when oxygen comes in through your blood or sugar, it goes down through the arteries into the capillary. It then crosses from the capillary into the interstitial fluid and then from there into the cell. When your cell makes carbon dioxide and wants to get rid of it, it comes out of the cell into the interstitial fluid and from there into the capillary, into the intravascular fluid. So this is how your fluid is set up in your body. You got some in your cells, some in the blood vessels, and some around the cells, and you have to have the right amount for it to work properly.
Right. Okay.
So when it comes to for the body controlling sodium and water in the body, one of my pet peeves about Darwinism and evolution idea is that it's very unit or one-dimensional. It talks about, you got this gene, it makes this protein or a gene regulatory network and makes this series of proteins, but that's as far as it goes. The second dimension would be, how do those all come together to form a system or, a system that works or coherent interdependent systems. But then on top of that, which what we're going to talk about today is the third dimension of that life is not static, it's dynamic. Things are changing all the time. As in the case of the sodium and water, it doesn't stay where it's put. If it's just sitting in one dimension, it's moving around all the time. And in particular, there are some hard problems of life that the body has to solve. So, for example, you're always breathing, and with cellular respiration, when you get energy from the sugar molecule, you give out carbon dioxide and water. So every time you breathe out, you breathe out water. So the body's always losing water through respiration. All right.
Yeah. Okay. So Howard, this is I'm sorry to interrupt you. This is a really important point because, if you're sort of sitting back naively and saying, well, why don't we just get the amount of water and sodium that we need and just leave it? Let's not touch that. Once we've got it set, let's just leave it. But you're saying there's things that are going on in a living organism, in a living system, that require you to constantly balance that and adjust that.
Right. And that's why the body has to be able to control its sodium and water all the time, because for you to be able to breathe, you're always losing water, all right? Yep. For you to be able to control your temperature, you're always perspiring. So you're losing, in your sweat, you lose sodium and water, all right? For your
Okay.
gastrointestinal system to work, it's always secreting sodium and water and then bringing some of that back. But technically, you're losing sodium and water from your GI system. And most importantly, your kidneys, they get rid of toxic nitrogen products that are byproducts from protein metabolism. So as they filter the blood, that's bringing sodium and water into these microtubules, and then they bring back a certain amount of sodium and water. And certainly in your urine, you're losing water and you're losing sodium. So you have these four systems all the time between the respiratory system, thermoregulation through sweating, the gastrointestinal system, and kidney control of the sodium and water in the body. You're always losing sodium and water all the time. And then on the other side of the equation, right, you have these thirst and salt centers in your brain that are telling you to drink water, bring in fluids, and take in salt. And the GI system absorbs all of that. So there's no control of that. Whatever you take in, whatever water you take in, whatever salt you take in, the gastrointestinal system absorbs it all. It's not like the way it controls calcium or iron. So you've got all this going on at once, all right? You have to have enough water in the cells, enough water in your bloodstream, and the sodium has to be, make sure the sodium pumps are keeping sodium out of the cell. And at the same time, you've got these four systems keeping your body alive for breathing and gastrointestinal system and temperature control and making sure you're taking care of the nitrogen, toxic nitrogen products. And then you're bringing in salt and water all the time. So you've got this in and out all the time that you got to try to manage.
Yeah. So I think we all know that when we exercise, we're supposed to, make sure we're hydrated and drinking enough water. My wife did the Tough Mudder a little while ago. And at the beginning of the Tough Mudder, they said, now everybody make sure you got your sodium tablet, right? So they were recommending that people have a little bit of extra sodium that they could absorb as they go through this multi-hour exercise event.
That's because while you're sweating, you not only do you lose water, but you're losing sodium in that water. There's sodium in sweat. So that's what's so important.
Okay, so with all that in hand, Howard, and understanding these ways that sodium and water are lost, how do we go about controlling this?
Yeah, so to control anything, you have to remember that you need a sensor to be able to sense what you're trying to control, an integrator, and an effector. The integrator takes that information from the sensor, decides if something has to be done, and then it sends information or sends orders to the effector. So the first thing we have to figure out is what kind of sensor are we going to use? How are we going to be able to sense the sodium and the water in our body? And you have to ask yourself, what component of the body, what we've just talked about, that is associated with the sodium and the water, and that's the extracellular fluid. But through that, obviously the arterial blood volume is dependent on sodium being outside the cell with water. Now, yes, you have a lot of water in your cells, right? But there's not much sodium there. The key thing to remember in biology is wherever sodium goes, so goes water. This explains it. Maybe you've always wondered and said, well, how come the doctors say if I have high blood pressure or I have swelling in my legs or I have heart failure, how come they tell me to watch how much sodium I take in? Where does that come from? What's that about? Well, this is the reason, all right? The more sodium you have in the body, the more water the body holds on. The body holds on to more water because of the sodium pump pushing it out of the cell, keeping it in the extracellular space, and therefore into the arteries, and that's why you can have higher blood pressure, and it can aggravate heart failure. So the arterial blood pressure or the volume is really the sensor. That's the area. That's the thing that may give us some information. The question becomes, what kind of sensor are you going to use? Well, when the heart pumps, right, and the heart pumps blood through the arteries, it causes blood pressure. I mean, when I check the blood pressure in someone's arm, the arterial blood pressure is technically it's the force applied by blood against the brachial artery in that arm, right? Again, and so it stretches. In this case, it stretches the wall. If you could put a sensor there to detect that against the artery, that would give you some information about the arterial blood volume. I mean, technically, all the blood vessels and chambers in your body have a quote unquote blood pressure. You have a certain amount of stretching of the artery in the brachial artery, but down in the arterioles, in the chambers of the heart, so they all have some sort of blood pressure. But technically, the arterial blood pressure that doctors talk about is the one in the brachial artery in general.
Right. So when you go to the doctor, every time I go over there, they put it around my forearm, or not my forearm, my upper arm.
Right.
Okay. So Howard, this sounds very non-Darwinian to me. I mean, Darwinism talks about, the environment, pressuring the organism and causing things to happen. But you're talking about the organism sensing its environment and having, active sensors that say, hey, what am I experiencing here?
Exactly. This is the interior environment. The body has to make
Exactly.
sure the cardiovascular system is sending enough. It has to have enough arterial blood volume to have enough arterial blood pressure to be able to send enough blood, to have enough blood flow to the tissues. Otherwise, you go into shock. Now, there's different reasons why people can be in shock, have low blood pressure. You can have cardiogenic shock where the heart isn't pumping well enough. So that's another effect of blood pressure, how well the heart works. You can have septic shock where the downstream arterioles just dilate because of toxins, and suddenly the vascular resistance is markedly reduced. So every time the heart pumps, a lot of the blood's going into the tissues, and so there's not enough blood staying in the arterial system. And then on top of that, the blood pressure is also dependent on the arterial blood volume. So you really have three factors here in the artery, in the brachial artery: the cardiac output, the downstream or systemic vascular resistance, how tight are the arterioles down there blocking the blood from going through, so it takes a while to get through, and then the actual amount of volume of blood, which is related to how much water and salt you have in the body. So you got these three factors that the body's always dealing with.
Mm-hmm. And I want to make sure we didn't gloss over this. You're saying there's an actual molecule or set of molecules within the arterial wall that detects when the arterial wall is being stretched. Is that right?
Well, yeah. So that we're going to get into those the four systems. I'm only going to mention four systems in the body that overlap with respect to controlling sodium and water in the body. All right. So the first one that we want to talk about is the sympathetic nervous system. So you have what's called baroreceptors. You have sensors in the main arteries going up to your brain in the main artery, the carotids. Okay, and they're always detecting what the blood pressure is based on the stretch of the blood vessel. All right. Now, this becomes very important if you bend over and you're working in the yard, and then you stand up very quickly, you'll notice you get dizzy, right? And that's a sign that the blood going to the brain has been reduced. There's global lack of flow of blood to the brain, and that's why you get dizzy. And that's because the blood pressure has dropped for a few seconds. And it usually goes away in a second or two. Well, it's the sympathetic nervous system that solves that problem. It detects this drop in blood pressure, and it sends a message to the brainstem, and the brainstem reacts to it and sends out a hormone or neurohormone called norepinephrine. And that not only makes the heart pump harder and faster and increases the systemic vascular resistance to increase the blood pressure, it's thought also to move some of the blood from the veins to the arterial system. And on top of that, it goes to the kidneys and it tells it to start holding on to salt and water as well. So that's one, and it also ultimately tells you to start eating, to drink water and take in salt. So that's one system. It's a very quick system, is very important for you being able to stand up. I mean, we couldn't be bipedal.
Yeah. Okay, so hold on, slow down here for a minute for me. So we've got these receptors. Now, were you mentioning that these receptors are in the brain? But that's different than the mechanoreceptor that you were talking about in the brachial artery, right?
No. I was referring to, just in general terms, what you want to do is, if you're going to be trying to detect the blood pressure, you need to have a mechanoreceptor, a stretch receptor somewhere in the arterial system.
And so then you're saying there is such a thing in the main arteries in the brain?
Right. Yeah, they're called the baroreceptors, which refers to blood pressure. Yeah.
Right. Okay. And that's triggering a hormone that gets sent out, which does all these other things like making your heart pump faster and contracting the muscles and so on and so forth that you mentioned.
Right. And it's a nerve. So it's neurohormonal. So it happens in a split second.
Which is
it's
fast.
Happening
Okay.
very,
So that
very
one's
quickly.
really fast. Now, is that all that we need, or are there other?
Well, interesting enough, then there's another system in the kidneys, okay, at the arteriolar level. So each kidney has about 1 million nephrons, and as the blood is entering into each of these nephrons to be filtered, it goes past a sensor there as well that detects how good the flow of blood is as well. It's called the renin-angiotensin-aldosterone system, RAAS. But basically, what happens is, there's a sensor there, and if the blood flow reduces, it sends out a hormone called renin. Renin eventually gets transformed into a hormone called angiotensin 2. And angiotensin 2, it goes to the arterioles and it tells it to contract, so that increases the blood pressure, but it also goes to the adrenal gland and it tells it to send out a hormone called aldosterone. And aldosterone is the hormone in your body that tells your kidney to hold on to sodium. And it also goes to your brain and says, eat salt. And between all this, it also tells you to take in water and salt. So that's the second system. So you've got the main arteries going to the brain, and in the carotid they're detecting the flow of blood through there. Now you got the arterioles in the kidney, in each of the nephrons that are able to detect the flow of blood there, and they are just, and it's an inverse relationship. If the blood pressure drops, it increases the renin.
Sure. Yeah. And do you have any idea? I mean, do we know how they're able to detect the flow?
Well, it's thought to be a stretch receptor, just like when if you put your hand on on the hose, right? And if the water is going through the hose, is going through more power, you're going to feel that stretch. Just like you have a stretch receptor on your skin, right? You can feel there's this Pacinian, and I try to remember the other corpuscles. There's these different sensors that, with movement of the wall in that area, with movement of the wall of the artery or the arteriole, that stimulates a nerve that sends a message. Well, first for the one in the arteries in the neck, that's going to the brain. Here in the kidney, it's having a direct effect right there. The integrator is right there. It's reacting to this change.
Yeah. Okay. But you think it's also based on stretch, or what we would say literally physical distance?
Yes, a physical movement. Now, some people, they wonder if that sensor in the kidney can actually detect the sodium level as well. So it's if you look it up, there's really, I don't think they're 100% sure. They just know that there's a sensor there. It's sending out this hormone. The hormone ultimately tells the adrenal gland to send out aldosterone, which tells your body to start holding on to sodium. Sure. Now, I want to point out something here, and this is the key thing. You notice for these first two systems, they're telling the kidneys to hold on to sodium, right? It ultimately holds on to water too. But the key thing here is, like, the body knows it's sodium, right? That keeps water follows sodium. It's sodium that's so important because of the sodium potassium pump, sending the sodium out of the cell, keeping in the extracellular fluid. And so these systems are keying to sodium, not necessarily water. You know, I remember in medical school, well, where did this come from? I would think it would be controlling water, but water eventually, because wherever sodium goes, water goes automatically in the body. So these systems are keying. Aldosterone controls sodium, not water.
Yeah. And both of these systems also, I just want to circle back to something that we had mentioned earlier. If you look at this from an engineering standpoint, you've got a sensor, and presumably it's checking against some kind of a baseline, right? There's an integration aspect that says, this is where we ought to be. And we don't need to get into all the details there because that can get pretty complicated. But there's a sensor, there's a baseline or an integration or analysis or logic control. You might call it that way, a logic.
It has to have a set point of some sort.
Set point is another great term, yeah. And then there is an effect, right?
Exactly.
That it results from, okay, we've realized that we need to take in more sodium. And so we're going to send out this hormone, or we're going to send out this other molecule that causes us to take in more sodium.
Right. And what I neglected to mention is both the norepinephrine and the angiotensin II, they only do their job by attaching to a specific receptor. All right. So the norepinephrine in the heart, in the arteriole, in the kidney has to attach to a specific norepinephrine receptor. Okay. Same with the angiotensin II. It has to attach to an angiotensin II receptor in the arteriole and in the adrenal. So the adrenal sends out aldosterone, and aldosterone has to attach to an aldosterone receptor in the kidney. So none of these are floating around just doing their own thing. Okay. They have otherwise you have to be able to control this. So it attaches to a specific receptor. And of course, they only have a certain half-life. They don't last, the norepinephrine may last a minute or two. The aldosterone may last maybe 4 or 5 minutes. Otherwise, you're not going to have moment-to-moment control. You send this stuff out. If it works for 2 or 3 hours, you've lost your control.
Interesting.
So that's all of what's going on, yeah.
Well, isn't that convenient, Howard, that they just happen to have the right connections there with those receptors?
Yes, they're right in the right place where they need to be. Yes, yeah. Like Steve likes to think, they're not sitting in the spleen doing nothing. Okay, in the liver, they're right where they need to be. Yeah.
He's always complaining about the spleen, but okay. That was the first half of my conversation with Dr. Howard Glicksman about the remarkable control systems in our bodies that fight valiantly to keep us alive against the normal degrading tendencies of physics and chemistry. Join us again next time as we dive deeper into additional systems within your own body that help control water and sodium, both absolutely critical to keeping you alive and listening to us here at ID the Future. Until next time, I'm Eric Anderson. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.